IREC 2021 team number 105. We are Space Technologies and Rocketry at UC Berkeley. This is our mission concept of operations overview. First, our rocket begins on the launch pad. Next, the rocket undergoes propulsion. The motor is ignited and the rocket lifts off. The rocket undergoes powered flight until it reaches coasting. Then the rocket coasts until it reaches Apogee. At Apogee, the Drogue parachute deploys and the rocket descends under the Drogue parachute. Next, the main parachute deploys and the rocket descends until it lands and is then recovered. Airbears was a vehicle subscale of our IREC rocket Bear Force 1. Airbears was used in order for our team to gain experience. Airbears was made of blue tube and had a 75mm motor mount and employs a redundant dual deploy system. The payload used in this vehicle also acts as a ballast. Airbears was built from blue tube. Bear Force 1, our IREC 2021 vehicle, is made of fiberglass. This decision was made as the vehicle must withstand greater forces, and we also saw this as an opportunity to familiarize ourselves with fiberglass airframes. In Bear Force 1, both the coupler fit, rocket wobble, and mass distribution are improved in comparison to Airbears. The nose cone of Bear Force 1 is made up of wound E fiberglass with an aluminum tip. The nose cone has a 5-to-1 ogive shape. It interacts with the payload stack via 4 632 screws and is secured by weld nuts and leaf springs for a rigid connection. Next, the booster tube of our vehicle will be explained. Our motor mount assembly consists of 5 main parts: the motor mount tube, motor casing, the motor itself, the motor retainer, and centering rings. The motor mount tube is 98mm by 33 inches and is made of craft phenolic. The motor casing is a 98 10240 Aerotech RMS casing with closures. The motor we decided to use is the commercial M2500T. We chose this motor as it allowed for the payload mass, velocity off the rail, and apogee that we desired. Shown is a thrust curve for the M2500T motor. For motor retention, we used a 6061 T6 aluminum thrust plate and a 98mm flanged motor retainer. The flanged motor retainer was screwed into the thrust plate. The centering rings we used are 4-inch by 6-inch G10 fiberglass. The fins we used for our vehicle are made of 1/4-inch E fiberglass and were made via water jet cutting. The fin dimensions and geometry can be seen on the right of this slide. Fin fillets between the fins and the booster tube are used. The fillets are made of epoxy that is reinforced with carbon fiber. Fin flutter analysis was performed on our fins. It was noticed that the fin divergence speed was below our maximum rocket speed. So we performed tip-to-tip fin glassing with 6-ounce fiberglass sheets and epoxy in order to increase the strength of our fins. There are 2 main types of fasteners used in our vehicle. We have in-flight separation points and in-flight fixed points. In-flight separation points occur at the payload tube and Avionics Bay coupler interface and at the Avionics Bay coupler and booster tube interface. At these in-flight separation points, 3 4x40 by 5/16 inch nylon shear pins are used. In-flight fixed points consist of the nose cone shoulder and the payload tube interface. Here, 4 6x32 632 by 1 1/8 inch black oxide alloy steel screws are used.
The recovery section is responsible for ensuring the safe recovery of the rocket such that it can be reused in the future. The Avionics Bay structure is located within a 6.5-inch section of body tube. The structure contains 2 aluminum outer bulkheads and 2 inner bulkheads, which consist of a piece of 3D printed PLA epoxied to a wooden bulkhead. These combined inner bulkheads act as a housing for the sled. All bulkheads are toleranced to fit within the tube during assembly. The bulkheads are then fastened to the airframe with epoxy, and the structure is secured using threaded rods. The tube also contains a 5 by 1.49-inch door used to access the electronics. Wire holes were drilled through the bulkheads for wire management, and the bulkheads provided one mounting point for P-clamps for the wire harness. The Avionics Bay sled was designed to maximize accessibility during wiring. It is for this reason that a removable sled design was chosen. Our sled is symmetric, and it contains 2 inner compartments which house the 9-volt batteries. The altimeters are located on the outside walls of the sleds. These outer walls also provide an additional point for attaching P-clamps. The sled then slides through the door in the tube. It is toleranced for friction fit, such that the sled is secure during flight, but easily removable. The outer aluminum bulkheads are attached to galvanized steel U-bolts. The parachute's shock cords are then attached to these U-bolts using steel click links. Black powder charges are also attached to the U-bolts, and these charges are used to separate the rocket for parachute deployment. The Avionics Bay electronics consists of 2 perfect flight stratologger altimeters. Each altimeter is connected to a 9-volt battery, a switch, and 2 black powder charges. One charge is at the top of the booster tube for the Drogue parachute, and one at the bottom of the payload tube for the main. The recovery system contains redundancy. The main is set to deploy at 1,000 feet, the redundant altimeter programmed to 900 feet, and the Drogue is to deploy at Apogee, with the redundant altimeter programmed with a 1-second delay. The same electronics were used for the redundant system in order to prevent user mistakes. Both parachutes are free-to-shoot Iris Ultra elliptical parachutes. The Drogue parachute is 36 inches in diameter and the main is 120 inches. These sizes were selected in order to minimize the kinetic energy on impact while also minimizing the drift after deployment. These are trade-offs that were optimized by the recovery subteam. Both parachutes are held within 30-inch fiberglass couplers. The black powder charges used for separation of the rocket were as follows. The main had a mass of 3.04 grams, and the Drogue charge had a mass of 3.28 grams of black powder. Redundant charges were used for both parachutes to ensure successful deployment, and all charges were oriented towards the center of the rocket.
For our rocket's payload, we chose to launch an experimental stack of 3 payloads inside our payload tube and 1 payload outside. The IRIS Muons project combines 2 originally separate projects into a 1U CubeSat unit to conserve space in the payload structure. IRIS records information via sensors, or IRIS for short, is a sensor suite PCB that records various flight data like acceleration, angular velocity, temperature, to assist in developing flight-critical avionics and validating current and future simulation work with respect to flight dynamics. The Muons payload tracks atmospheric cosmic ray intensity during flight by capturing muons, particles induced by cosmic ray interactions in the atmosphere, to investigate various factors influencing the atmospheric cosmic ray population. When a muon particle hits a scintillator plastic block, light is emitted. This allows a PCB to detect incoming muons. The goal of stabilization is to have a platform that can self-stabilize in the 3 rotational axes. This can be done using a sensor attached to the reference frame stationary to the rocket, a microcontroller, 3 servos, and a power source. Good stabilization itself isn't hard to achieve, but achieving our goal under the conditions of launch is where the challenges come in. In order to conserve battery, we have a photo relay integrated with our circuit, which ensures our servo motors only turn on and stabilization only starts once our main sensor detects a launch. We also need to make sure that the sensor is correctly calibrated at launch. So we repeatedly calibrate at an interval of every 10 minutes or so to ensure proper calibration before launch. Lastly, we need to verify how well our platform stabilizes. This involves a second sensor on the platform itself writing to a microSD. The microbial fuel cell, or MFC for short, is a bacteria-powered battery that takes advantage of the electrogenetic properties of Shimonella oneidensis during anaerobic respiration. The purpose of this payload was to test its performance during flight as a potential source of electricity. We measured MFC's voltage throughout the duration of the flight. We selected our MFC design for its simplicity, low maintenance, and cost effectiveness. Previous designs incorporated liquid culture medium and expensive and dangerous electrode materials. To minimize the effects of a potential failure, we settled on a mud-based fuel cell in a high surface area graphite fiber felt. An unexpected setback we faced was when algae started growing in the fuel cell in response to sunlight exposure. The algae outcompeted the bacteria, causing the fuel cell to stop producing any electric potential. All this is contained in an aluminum T-slot structure frame designed to be fully modular for easy assembly and adjustability. We can mount all three of the preceding payload projects into this frame, or we can substitute in steel ballast plates for any and all of the previous payloads, adjusting the center of gravity as we see fit. There is one last payload, and it's on the exterior of the rocket's airframe. The cameras project uses the Mobius Maxi camera mounted on a custom baseplate that is epoxied to the airframe's exterior with a custom shroud. 2 shrouds shall be mounted. The camera shrouds have been optimized to maximize field of view while minimizing impact to the aerodynamics of the airframe, allowing cameras to record the flight with as much detail as possible without being a detriment to vehicle performance. The recorded results are retrieved from an in-camera SD card post-landing. The captured footage documents the rocket in flight even after it escapes visual range from the ground. Here is the footage recorded from our most recent launch.